see a lot of faces ready to go to lunch. So I'm going to skip over some parts, and if there's questions about it, you can get to me offline.
Don't feel too rushed.
So I'm feeling very much like the outlier here in this group this year, as I have spent almost no time studying any planetary body in the solar system other than the one we live on. But I have done quite a bit of work studying organic compounds and what happens to them in hydrothermal systems, and particularly in submarine hydrothermal systems like the one shown here. And so this is a couple of places I've worked at. These are sites in the deep ocean, out in the mid-Atlantic ridge, in the middle of, out in the middle of the Atlantic. And these are hydrothermal systems that occur at the bottom of the ocean, and I think most of you have probably heard about these kinds of things. So the idea is that you have some magma welling up at the bottom of the ocean. It drives circulation of seawater through the oceanic crust where they come out at these hydrothermal vents. And part of the thing that happens during the fluid-rock interactions that go as these fluids circulate through the crust, the seawater, is that these systems become highly reducing. So they get really high concentrations of reduced species like hydrogen and methane. And what drives these systems, these particular kinds of systems that I just showed you here, is a process called serpentinization. I think most of you have probably heard about this, where you have reaction of olivine and pyroxene with water to form serpentine, brucite, and magnetite. And one of the big products of that is, subproducts of that is hydrogen. And that hydrogen is generated as ferrous iron in the host minerals, reacts with water to become ferric iron that is deposited in product minerals, and it releases hydrogen. So different things go on in hydrothermal systems, and one of the things that goes on is potentially is abiotic organic synthesis. So in these highly reducing environments, the reduction of CO2 or carbon monoxide to methane or other kinds of hydrocarbons is pretty much thermodynamically favorable because of the high hydrogen concentrations. But there's other things that go on at the same time, organic decomposition reactions, where organic compounds can then decompose owing to the higher heat, and then you can also have different transformations of organic compounds. And in most hydrothermal systems, you get a mixture of these two different things going on. So these kind of, I'm very interested in whether we can take some of the lessons we learned from these terrestrial environments out into the solar system and see similar kinds of things, and what it might be able to tell us about what's going on in hydrothermal systems elsewhere. And in a lot of places out in the solar system, we're probably seeing hydrothermal processes being driven by the same serpentinization process, so we expect a lot of the same kind of chemistry. So we've been talking a lot about meteorites or meteorite parent bodies, and I think that's kind of a good environment where these terrestrial systems might be able to inform us something about. And I guess my kind of maybe naive view of organic carbon in these meteorite parent bodies, there's really two kind of inputs here. So you have what is originally accreted from the primordial materials in the solar system that gets in there, and then you have some modification by hydrothermal and other processes. And I think a lot of the debate is the reason to study these things is try to figure out which of these processes are responsible for different kinds of compounds. And so we've already talked in this workshop a lot about meteorites, so I won't belabor the point, but one thing is you do see a large assortment of organic compounds of different kinds, different flavors, plus this insoluble organic matter. And again, you know, the question I think is whether these kinds of organic compounds, you go to a particular kind of organic compound like an amino acid, is that something that was accreted with the original materials, or is it produced by something that came later on? So to go back to these natural systems here, so again, the reducing conditions that are present in these environments make organic synthesis a favorable process. I'm going to be talking mostly about organic synthesis today. So I won't get too much into this in the interest of time, but basically, anytime you write a reaction from CO2 plus hydrogen plus nitrogen or other inorganic things to some organic compounds. In these kind of environments, that's thermodynamically favorable. So any reaction like this has a free energy or it gives energy less than zero, which means it should go forward in these kind of environments. And there's different kinds of mechanisms we can think about these kind of reactions going on. The one that's most commonly invoked in terrestrial environments is Fishertropes type synthesis. So most of you have probably heard about this. So Fishertropes, in its strictest sense, is a reaction of carbon monoxide and hydrogen to make methane and produces mostly hydrocarbons plus alcohols and carboxylic acids, things like that. So here's just an example of from a laboratory experiments where I've reacted carbon monoxide, hydrogen at 250 degrees C, and native iron as the catalyst. And this is organic extract. And what we see here, all these peaks here, is different hydrocarbons, so just long chains of carbon connected one to another. The numbers here is the chain length of that thing. And then there's also some alcohols here. And if I derivatize this sample, you would see a bunch of carboxylic acids following the same kind of trend. And one thing you note here is that if you go down in carbon number, you get increasing amounts. And because this is organic extract and we've lost the volatile compounds, but if you actually went down to carbon 1, this would continue going up through the roof there. So so you get more of the smaller things and then less of the progressively less of the larger things. If you do add some ammonia to these kind of Fishertropes kind of reactions, you do get amino acids, amines, and things like that that are of interest, particularly to prebiotic chemistry. And this is just an example of another Fishertropes experiment where they have added some ammonia in 370 degrees using some ground up Merches and Meteorite catalysts, and you do get a bit of amino acids in the mix of products from that. And there's a whole host of other different organic synthesis pathways. I won't go through all these things. If anybody's interested in these kind of things, they can see this review paper I wrote a few years back, which goes into details about a whole bunch of different synthesis pathways. One I will mention, because it's often cited as a source of amino acids in different planetary environments, is the Strecker synthesis. Reacts to aldehyde, cyanide plus ammonia, and it very effectively makes amino acids in aqueous solutions. And this has been studied for a long time, first discovered by this guy here, Strecker, in the late 1800s, and studied pretty extensively by people, particularly those interested in prebiotic chemistry. So that's kind of the theory and the laboratory experiment view of things. So what happens if we go out to these hydrothermal systems on the seafloor and look for organic compounds that may be abiotic? And people have done this for a couple of decades now, and one of the things they mainly believe the results that come out of this is it's really pretty much hard to find anything that looks abiotic in these natural systems. So so far, so it's a couple of decades of work, people have gone out to these things and looked for abiotic compounds. We don't see very much of them at all. So here's an example from these places, Lost City and Rainbow, that I showed in that last video. We go out and sample these fluids and do an extraction from the fluids, and what we find is, like at Lost City, which is at about 90 degrees C coming out of these things, what we see is just some alkanoic acids. The fact that these are 8, 10, and 12, so they're even carbon numbers, tells us that those are biological. So none of this kind of stuff you see for like a Fishertrope synthesis. This is a 360-degree system, a place called Rainbow, one of the largest, highest hydrogen concentrations of any of these systems. And again, we don't see anything like this. We see some polycyclic aromatic hydrocarbons. This is phenanthrene. This is a couple of derivatives. These are all, over here, are all just contaminants from the sample processing thing. But nothing like a Fishertropes product, nothing that looks abiotic. These compounds are made by pyrolysis of organic matter at high temperatures, so nothing that looks biotic or abiotic. We do see a little bit of abiotic products in light hydrocarbons. So this is from the same Lost City hydrothermal fluids, and using various different kinds of evidence, it looks like the light hydrocarbons in this system are abiotic. One of the things that tells us that is if you look at the isotopic composition of these light hydrocarbons, so this would be methane, ethane, propane, and butane, is that they become lighter as you go down in carbon number. If you look at any kind of pretty much every natural gas that's out there, thermogenic natural gases, the trend goes the other way. So this tells us there's something unique, and from different kinds of ways, we really believe that these are abiotic, but just these light hydrocarbons. And what these authors, Gior, Proskorowski, and all, propose that this is a Fishertropes type synthesis as from seawater rock interactions, so as the hydrogen builds up, you make hydrocarbons. Unfortunately, like the more recent information that comes out of these systems now, it looks like, and in fact, these things are not coming from these Fishertropes kind of products, but they're re-speciation of magmatic fluids at much higher temperatures that are just being extracted from the rocks as the fluid goes through them. And a couple of the reasons it tells us that is that this methane is C14 dead, so it's very old, whereas the seawater is relatively young. The CO2 in the seawater is relatively young, so the methane is not coming from that CO2 as it goes through the fluid. Also, you see methane concentrations in these fluids that are actually higher than the amount of CO2 in seawater, so it can't be coming from that source. And just briefly, I won't go through this, but that's in agreement with laboratory studies, really tedious year-long experiments where I've tried to simulate these systems, creates lots of hydrogen, but pretty much no other organic compounds. And a little bit of organic compounds that you do see are all contaminants, so you use a label carbon-13 inorganic carbon source, and none of that label comes out pretty much in the organic matter, so they're just contaminants. So experiments versus natural systems. So what is it, we see these experiments and theoretical things that say Fishertropes kind of things or other abiotic synthesis pathways should be favorable in these conditions, in these environments, but they don't seem to happen. And some of the reasons why it is laboratory Fishertropes type synthesis is really a process that involves gaseous reactions and really effective catalysts, usually things like native transition metals or transition metal carbides are used as catalysts, and it's very effective. But in natural systems, usually the reactants are present as dissolved aqueous species, so they're not gases, so they're probably not as reactive. And these kind of catalysts that are used in the laboratory experiments are pretty much not present in kind of hydrothermal systems. The other thing is that laboratory experiments often usually utilize very high concentrations of highly reactant reactants, so things like carbon monoxide, and in these like Strecker synthesis, you have aldehydes, cyanides. Usually in laboratory experiments, these are used, they use concentrations on the millimolar or molar scale concentrations for these things, but in any kind of hydrothermal systems, these kind of things are at nanomole or much lower levels. So it makes it much less effective. But if we think about something going on in the outer solar system, these kind of things are probably much more prevalent because conditions are more conducive to these kind of reactions going on. You have lower pressures, so you have a greater likelihood of having gaseous reactants present in the system, maybe a mix of gas and liquids. You have these kind of catalysts, sometimes native iron, native nickel, other kinds of things like that. And then you may have input of these things like aldehydes and carbon monoxide and formic acid that are very conducive to these kinds of reactions. So maybe in those kinds of environments, maybe these kinds of things pathways will be more favorable. So I just want to spend a couple minutes talking about the opposite side of this coin. So you have these pathways for organic synthesis, but in hot water, the other thing that really goes on a lot is that you have decomposition of organic matter. And this is particularly a concern for amino acids, because amino acids decompose pretty rapidly in water in hydrothermal environments. So that brings up the question of why do we see amino acids in these hydrothermally altered meteorites? So this is just an illustration of this. So this is an experiment I ran a couple years ago with amino acid norvaline. This is found in meteorites like Murchison, and put these things in hot water and they go away pretty fast. And they go even faster when you add minerals to the mix. So here's with no minerals, just an aqueous solution. Here's reactions with minerals. So if you put minerals in them, like you're going to see in a meteorite parent body, reactions going even faster. So these things should be disappearing over relatively short time scales. Even at 50 degrees, the decomposition of these things should not last more than a couple of years at most. This is some recent work from Aaron Burton, working with Danny Glavin and Mike Callahan. I've really been very much interested in this work, and they've been looking at the diversity of 5-carbon amino acids, and they show a very intriguing compositional variability among different kinds of meteorites. And they've done many more different kinds of meteorites than what I've shown here, but this is just some contrast. And you can see, and what's shown here by these bars is different amino acids families where the amino acid is in different positions. So here it's right next to this carboxyl group. Here it's a little down the chain, and progressively down the chain as you go right here. If you look at different kinds of classes of meteorites, you can see the distribution of these C5s is very different. So in these classes here, it's mostly these alpha amino acids, and down here, it's mostly the amine group is at the end of this chain. So you get this very curious diversity of these things. And so you have these different structures, and the question then becomes, are these different amounts due to different synthetic pathways? Is some synthetic pathways more favorable in one kind of meteorite than another, or is it due to difference in their resistance to decomposition? So maybe you make mostly this with only a little bit of this, but if this goes away much faster than this one, the more alteration you get, the more you get of these kind of things. So I think this may be a way that we can kind of use these compounds as a key to unraveling the source of organic compounds and amino acids and other related things in these meteorites, because these C5 compounds have enough structural diversity that you can look at different kinds of classes of compounds, and yet there are sufficient abundance to be able to measure. But in order to do that, if we want to use these compounds to unravel what the relative contributions of synthesis and decomposition to, we really need more basic information on these synthesis and decomposition pathways. And that's all I have today. Sorry to be rushed, but
So, questions? Yeah, right here, Simone.
So, I do have a few questions. I've been talking to Alexis Templeton and Everett Schock about the very issue of how we could produce organics on series, for instance. And so a lot of what you presented here is potentially high relevant to that. One of the issues that we were facing is the temperature. Some of the reaction, like Fishertropes, or some of the reaction that you're showing here, seems to require relatively high temperature, what we could potentially sustain within series close to the surface. And so, do you have a sense of how much wiggle room there is in terms of temperature and pressure conditions to get this kind of reaction going?
Well, I think it's kind of a misconception that Fishertropes requires high temperatures. It's certainly done that way in the lab a lot because they want to get effective synthesis, but it's something, the process that can actually go on at lower temperatures, get a little bit more competing reactions. But, you can go down to really low temperatures and still have these things go on. It takes a little bit longer to do it, especially if it's a gas phase kind of thing. And the essential thing about Fishertropes is you're making radicals, and the radicals are then reacting and other. And you can make those same kind of radicals with radiation also. So Fishertrope synthesis goes on in the cold interstellar space because you're making radicals by radiation rather than heat. So that's another way to make these same kind of products. It's a process where you're making radicals and the radicals are coming back together. So anytime you can make radicals, you can do that. But I've certainly seen Fishertropes done at temperatures of 100 degrees, and you could probably go lower. I don't know. It would be a good thing to test out experimentally, is what what the lower temperature limit is particularly in a kind of aqueous environment from thermal heating. But
you can just do it with radiation.
you can do it with radiation, yeah. You know, Monica Kress years ago talked a lot about that kind of process in the, you know, for the.
Tom, we have a question for you here at Survey Central.
Okay.
Hey, this is Penny Boston.
Yeah, hi Tom, this is Penny.
Penny.
One of the things that occurs to me when you're looking at natural systems like the hydrothermal vents, you do have very, very low concentrations. But this is because these are in direct contact with the open ocean floor. And if you imagine early planetary conditions on a lot of different bodies, you might have a roofed system where concentrations of those reactants would actually build up, and then you would change the kinetics, you would change the concentrations. And so I think that while we always appeal to natural systems on Earth, and I'm struck by the fact that the concentrations are so low, it's kind of surprising, there's also the presence of, you know, metals within those fluids, right? But they're not acting as a catalyst, as you point out, with a lot of these classic laboratory organic syntheses, you know, require. So do you think it's just simply the dilution of the system in the particular case of the hydrothermal vent that is actually not leading to these syntheses?
Well, you do make a good point that the early Earth may have been very different, and certainly there's more potential sources for reduced compounds or simple reduced compounds in the ocean, higher concentrations of those things. I mean, going back to the experimental work of Stanley Miller, where he made in the spark discharge experiments, a lot of the stuff that feed into these things, cyanide and carbon monoxide and methanol, things like that, which, you know, were produced in the atmosphere of his spark discharge experiment, then dissolved in his liquid water ocean at the bottom and underwent organic synthesis in that environment. So certainly there is a lot of that. But part of my point was these things like hydrogen cyanide and formaldehyde, those things have very short lifetimes when you start heating them up. Formaldehyde especially, you know, it's a concentration, you know, below 10 to the 9th in any sort of hydrothermal fluid. That's because it would rather be was much more stable as something like formic acid or methanol. So it decomposes really fast. So things like, you know, formaldehyde are not very good feedstocks for these things in a hydrothermal system, just because they react away very, very rapidly.
Just to follow up on that, I mean, in a hydrothermal system, the way they currently exist, these products are immediately impinged on by relatively cold seawater. You don't think that would preserve a certain, you know, amount of that material once it hit that thermal transition?
Well, maybe, but it's not that where they're unstable is in the hydrothermal fluid. So if you had a millimole formaldehyde in your seawater on the early Earth, and as soon as it went into the crust, it would decompose rapidly to formic acid. It's just not, and same thing with hydrogen cyanide. It wants to be something else.
Okay, thanks.
Those things, as soon as they started going through the crust, they're going to disappear.
Okay, thank you.
So you have a question in the chat room. You mentioned that the Fischer-Tropes reactions can take place at 100 degrees, and the question is 100 degrees C or K?
C. Well, that's the lowest temperature that I know somebody done an experiment with them. I wouldn't say that that's the floor. I think these things can go on at lower temperatures. It's just it does become a kinetic thing. You know, it may take longer, and people use. I mean, Fishertropes is something that mostly is studied to make gasoline. So, and it was, you know, invented to run Germany's tanks in World War II. So they want to make products fast. So it's almost always done at high temperatures. But I don't know that that's necessarily because it has to be at high temperatures. It's more just people want to see products.
Well, you have a question that's being typed in for a while now, so maybe we'll wait for that. But otherwise, we just announce now that we'll be back at 1 after
Yes.
lunch?
We'll be, yeah,
So that's
So-
about 50 minutes from now.
yep, we will start again with Maria's talk on